Welcome to our talk on bringing side channel power analysis to early SoC design stages. My name is Jean-Pierre. I work with NewAE, and Colin, we've did this work that we're going to present to you today.
Hi, I'm Colin O'Flynn, and you might have seen some of my previous work with Chip Whisperer, which talked a lot about side channel power analysis, what those attacks look like, and how they work. So this is pretty interesting because it's showing you how you can use some features that maybe you're already using, hopefully, but if not, they'll be really interesting to you in general, but how you can combine some of these features with side channel power analysis tooling to really understand what your design is doing and where you're going to see failures. So really briefly, I'm not going to go into a full background of side channel power analysis. If you're interested, I'll point you to our Chip Whisperer project, which is an open source project, has quite a few different tutorials and examples, and there's some chipwhisperer.io has some training material available as well. But to understand why you care about side channel power analysis, you need a little bit of background. So what we're basically saying is that digital devices take fundamentally differing amounts of power when they execute different functions. You can imagine basically, right, a multiply operation versus a no-op might have a different power signature. And what we do with power analysis is we actually measure this. So the diagram on the left of the slides shows the sort of very abstract way this works. We have a microcontroller. This microcontroller is executing code. And at the same point, we measure a power that the device is using on every clock cycle. So we don't need exact power. We're just getting a sort of arbitrary difference between two different stages. And the figure on the right shows an example of a password check where there's a number of incorrect passwords being tested and then one correct password being tested. And what you can see is up until sample point maybe 50, so on the x-axis is number of samples, there's no divergence between these two paths. After that point, you actually see a divergence between the sort of brown and gray paths. And what's difficult to see in this figure is there's actually multiple paths overlaid on the brown, but you're actually seeing multiple failed passwords. And in this case, it's actually one single character of the password that's wrong versus one single character that's right. So by monitoring the power, we can actually understand how far into a certain algorithm our code has run. So this is interesting. Password checks are really obvious, but RSA can be frequently broken in a similar manner. Even pretty recent implementations of it can be vulnerable to this. Even more powerfully, differential power analysis uses minute differences in the actual power being related to the data process. So even if it's the same operation with different data, if you put a number of ones over a data bus versus number of zeros, actually has a measurable amount of power difference. And so you can play with all that if you're curious. If you don't believe me, our Chip Whisperer project has a number of recorded traces. And again, it's open source, so you can go do that right now if you want. And how powerful is this in real life? Why should you care? Well, it's really powerful. So this is a AES 128 implementation. I think some of them we use, for example, embed TLS. So these are real implementations. And in under 100 encryption operations observed, so observing the function encrypt or decrypt data 100 times, with a software implementation can often recover the key. With a basic hardware implementation, you might be talking 1,000, or to 10,000, somewhere in that range, but it's still a very reasonable amount of data that you're observing. We're not talking that this is taking days, at best hours, maybe minutes of attack time. So this figure here shows an example of the output of one of these attacks, and in red is the correct encryption key, and for every byte it's ranking the correct encryption key. So you can see some of these red bytes are at the top, meaning they're the most likely guess is actually matching what the real encryption key was. Some of them aren't quite there yet, but you can see at the top left in gray there it says finished traces 10 of 20. So we're actually only observing 20 encryption operations, and we've already recovered quite a bit of the key. So some of this is being formalized. If you've done, secure devices, you'll already be familiar with this. But there's the new version of FIPS 143 is actually going to have side channel power analysis as part of the requirements. So it's something you definitely want to get sort of some background in and involved with if you're not already looking at it. All right, so that's side channel power analysis. What we want to do is we want to push side channel power analysis early in the design cycle. So we all know that fixing bugs, at the design stage is a lot easier than if you try to fix a device in the field, yet alone if we're talking ASIC and, you've already done the hardware. It's going to be really expensive now to fix. If you're fixing it while you're FPGA prototyping, well, that's great. That's really easy to fix. So this is what we're trying to do, is we're trying to show you that you can push this really early in the design cycle and still get really useful results to understand what your system is doing. And basically, defending against these is hard. This is really the problem of like the compilers weren't really designed with these leakages. So the leakages are very, very fundamental. The compilers aren't designed with them. Doing the mitigations, right, can be expensive. So you want to make sure you're doing correct mitigations, or you want to understand how much you need in terms of mitigations, because it's the classic example, right? If you build a really strong door, if you build a bank vault and then you put a $2 padlock on it, well, that was dumb. So with all of embedded security, it's all about balance, right? You could have the best side channel protection in the world, but there's some other problem. Or likewise, you have the most secure debug access system, but all the keys can be leaked and recovered really easily. So it's all about balance between the various security measures you're implementing. So if we do these earlier evaluations of the side channel results, you get a lot better results in terms of your countermeasures, in terms of where you're putting this effort. And again, the objective here is let's make this easier to do. A lot of what we've looked at before, so if you look at some of the examples, deal with sort of software implementations or deal with looking at existing chips. And this is going to talk a little bit more about the use of DesignStart and use of sort of those FPGA prototyping platforms. So if you were to do this right now with everything existing, if you go to Chip Whisperer, you say, I'm going to run this on my FPGA system on a chip, you can do that. That's not a problem. The current approach with Chip Whisperer is it uses a trigger to tell Chip Whisperer when is some code of interest. So code of interest being encryption operations, security checks, something like that. So we basically have this special trigger mechanism, and by special, I mean it's a GPIO pin going high, so not super high tech, but it works really well. It's really easy to do, and you can run it on any system. And this tells Chip Whisperer at this point in time, there's some interesting data. Please record some of the power at this point to analyze it. So we need to tell Chip Whisperer roughly when it happens. We don't always need perfect triggering. We can deal with that later in post-processing. But we need at least a pretty good idea, ideally a perfect trigger. So the GPIO gives us that. There's no jitter. It's very specific. There's code executing when the trigger runs. So this works really well. The bad side, right, is that this is fine if I'm just testing one single function or a few functions, because every time I want to change where I'm looking, I've obviously got to recompile the code. The issue with this is that we, are changing the code as it's running, so we're changing the code when we recompile it. But we also need a dedicated pin. So when we're talking SoC designs, right, maybe you don't actually have the GPIO peripheral up yet because you don't actually need it for anything else. So there's some also disadvantages when we talk specifically about this early stage SoC design. What this looks like, so this trigger issue, by the way, and what you can see here is this is several power traces overlaid. So you can probably see if you look carefully, there's some small variations in the power, and these small variations are actually what enable us to do side channel power analysis. But you can see everything's overlaid really nicely. So this was being done by a GPIO trigger. Again, if we don't have GPIO, what can we do? And this is where we've done a lot more work from here that's going to be really useful for early stage SoC designs. And JP is going to talk about this. This is actually using the trace mechanism that's present in many of these designs to actually do the triggering and do some other analysis work. So I'll hand it over to JP to give you all the fun about using trace for this type of work.
Thanks, Colin. Right, so instead of using the trigger GPIO, you can actually use trace to get notified when the execution of the program reaches any address that you care about. So here we've got the same firmware code, and in this case, the trigger high is still present, but is not really needed because what we're going to do is say at the address 4AE, get the ETM, that I'll explain a little bit later, to emit a trace packet that tells you this is where I'm at. So that has a lot of advantages, right? It's completely non-intrusive because the trace logic that is present in the ARM processor is running completely independently of your actual code, right? It doesn't alter your code path at all and lets you target arbitrary addresses without any recompilation, which, as Colin mentioned, would be kind of annoying to deal with otherwise. And also uses your existing debug infrastructure that you're using to develop your application, so you don't need any extra pins or anything like that. So that's all really great. There's one set of disadvantages, is that unlike our trigger high GPIO, which is rock solid and it's going to be at the exact same time every time you run it and allows you to do the trace overlay that we showed in the previous slide, with the trace packets that you get from this, you're going to have a little bit of jitter, a little bit of latency, or perhaps a lot of latency. So trace isn't perfect, but we can still do some really neat things with it. That's really what all this presentation is about, is to show you exactly, well, what can you do with it? So if you're familiar with trace, you probably have some notion of what it's used for, right? It's used for instruction tracing to help you debug, get your full execution history as you're developing your program to understand why maybe something didn't work as it should, where it went off the rails. What we want from trace here is something that's completely different. We want a lot less than full execution history. That'll help to minimize the jitter and latency, by the way. We just want, in this case, in this basic case that we're building from, we just want the indication that a specific instruction has been executed with as less jitter and delay as possible. So in order to do that, because trace is a term that encompasses a lot of technologies, if you're familiar with it, there's various acronyms, of course. But to get these kinds of packets that we're talking about, you need two things to be present in your target processor: the data watch point and trace unit, and the embedded trace macro cell. Everything that involves ETM is pretty complicated because ETM is so powerful. But for what we're doing here, once you have the recipe, it's pretty simple. Now, our target that we use for this work here is the DesignStart FPGA package that ARM released a while back. If you're not familiar with it, it's kind of like a reference design that's meant to be used on the popular Digilent ARDI FPGA platform. And it allows you to instantiate either a Cortex M3 or a M1. The M1 doesn't support this trace stuff, but the M3 does. So when you bring up Vivado with the instantiation of the M3, you can turn on the DWT, ETM, and more. And then to get these packets at a high level without going into the code, you basically need to set 3 debug registers. The one that sets the address that you're looking at, another one that sets the comparison function to say trigger when you get to that address, and finally in the ETM you have to do some enabling of these comparators so the packets can come out. So the DesignStart FPGA platform. So like I just mentioned, the DesignStart FPGA package is provided as a reference kind of design for the Digilent platform. And it comes, by the way, if you haven't seen it, with some excellent set of tutorials that show you how to get up and running. What we've done is we've taken that and kind of ported it to our own FPGA side channel analysis and evaluation platform. It's really not that different from the ARDI platform. It's got an FPGA. We just added all these extra side channel goodies to it, like the ability to monitor power in a way that's fairly accurate, and the ability to do some glitching to do other types of attacks. We've posted already some detailed instructions for how to port the DesignStart ARDI design and methodology to our FPGA. And by the way, this is the platform that we use for this work here, but all of this can be applied to any platform as long as you've got a trace port, and as long as you've got an FPGA to house the trace sniffing logic that we'll talk a little bit in a few slides. So what are our requirements to do the kind of stuff that we're going to show in the next few slides? So we have some fairly unique requirements, like I alluded to earlier. So what we really need is some very accurate, cycle-accurate timing information for trace events. And we want time information that's relative to some stable reference, such as a trigger, event that's instrument and source code, or define trace limit. Now you might say, oh, wait a minute, I thought you started all this by saying we want to get rid of the trigger high. And that was our original motivation. And as we went along further in this work, we saw that, yeah, that's one thing we could do. We can also do a lot more. And for some cases, it's nice to keep the trigger high if it's available, because having that cycle accurate, jitter-free, stable reference lets you do some really neat things that I'll show some examples of. But it's true that it's not necessary, right? You can still do what we showed in the first slides, which is to say, generate an ETM packet when the AES encryption kicks off, no trigger pin necessary. So there's a lot you can do. It depends on the specific requirements, what you want to do, and we're going to show a whole bunch of examples to let you kind of visualize better what's possible with this. So the trace logic to look at what's happening, what's coming out of the trace port, what we've done was actually co-located that on the same target FPGA, which is housing the target Cortex-M3 processor. It actually requires very minimal logic to do that. It's not very complicated FPGA code. The trace data can come from either the parallel trace port, which is preferred because it's higher bandwidth and therefore less jitter, or the SWO pin, and both are available with the DesignStart design. Here's the link for our reference open source design, which was used for all the examples that we're about to show. So we're going to now run through a series of a number of different examples. These are like the things that we've thought of. Here's cool things you can do with trace as it relates to side channel analysis. This is just scratching the surface, though. So let's get on with it. So all these examples were done with exactly this setup that we're showing here, just to make it really clear. So like I said, we've got our ChipWhisperer 305 target FPGA board. That's the red board on top, and it's got the FPGA that's housing both the target processor and our trace collecting and sniffing logic. Connected to that is our ChipWhisperer Lite platform. Now, all that it does really is collect power traces through the SMA cable that you can see there, and it controls the target firmware in terms of saying, here, go do an AES encryption. Both of these are connected to your host PC, which orchestrates everything, and after the operation has been kicked off, the host PC gets back the power trace, the ARM debug trace, and can do all sorts of neat visualization and extracting of information to enable your side channel evaluation. So first example, now, in this case, what we've done is we said, well, okay, well, instead of just using the ETM PC address notification packet to kick off something, let's keep our trigger high. So that's what starts the power capture. And let's use the PC matching function to get notified when a particular instruction gets executed. So here we're running AES on the Cortex processor. So this is capturing the power trace of the AES encryption, which took about 5,000 clock cycles. We're doing 4 power samples per clock cycle. AES, if you're familiar with it, has 10 rounds. So we can kind of see that periodicity in the red power trace. You can see that there's 10 things happening at a macro level. Now, what trace allows us to do is label with these vertical black lines when this precise instruction, generated an ETM packet. So now you can get very, very detailed as to what's happening now, which I think is very cool, because that shows you a whole lot more than what you could see from just the raw red power trace. So that's kind of the one very simple basic thing you can do with that. You can go a little bit further. Now with the PC address matching, you're able to actually specify 2 different addresses on which you will get PC matches. Now you can change these over time, of course, whatever you want, but for a given execution run, you're limited to 2 addresses. So you can say, okay, well, how about instead of just plotting a specific address, let's look. This is one of again, this is AES encryption. One of the parts of AES is doing a shift rows operation. And so here we're highlighting the start and end of these by just having picked the start and end addresses of that function in the code. So here that, again, gives us an awful lot of information we didn't have before. Beauty of traces, this is done without having to instrument our code in any way, right? This is a single measurement. This is a single one AES encryption. We have ETM running alongside it and tells us this is what happened. This is where that code is running. So that's really cool. Now, in this case, we were looking at the AES shift rows operation. We have, in this case, there's 10 rounds, but there are actually 9 executions of the shift rows. So we could do different things from that. We could say, okay, well, let's overlay all the different shift rows executions, because perhaps that's something we want to build our attack upon. So in this case, you can see that 8 of the 9 traces actually perfectly aligned. And there's one of the traces which is shifted in time because of the jitter of the ETM packet, but that could be easily corrected in post-processing. Now, AES, like I said, it was about 5,000 clock cycles. Okay, that's something. If you're familiar with public key cryptography, that runs into the millions of clock cycles. So now on the same M3 processor, we're now running a 256-bit curve, elliptic curve operation, which took on the order of 10 million clock cycles, right? So now if you're looking to find stuff in there from a raw power trace, good luck, right? But, trace to the rescue, in this case, we're labeling exactly when the point addition operation of the elliptic curve operation is executed. And there's 256 of those because it's a 256-bit curve. So this could give you a tremendous amount of information. One thing we haven't talked about yet is timing attacks. So you can attack a target based on the power consumption. You can also perhaps attack it just based on the fact that the time to do a repeated operation depends on, for example, perhaps specific bits of the 256-bit key. In this case, once we've collected these time samples of the point addition operation, we can actually very trivially see that what's the time delta between successive operations. In this case, it's quite high. So perhaps there's something here that could be exploited. And this you would have had a hard time to do from the raw power trace without the ETM instrumentation information on top of it. Another thing that you can do with it, there's something called test vector leakage assessment, which is a statistical tool that tells you where in time side channel leakage might be occurring. And it's standardized by ISO. It doesn't actually break the security. It just is a statistical tool that tells you where it's likely that leakage might be occurring. So you can see where this is going. The output of the TVLA test is a time-based waveform, and whenever the waveform exceeds a certain threshold, it tells you this test failed. So you'd be interested, of course, as a developer to know when this happened, right? So trace to the rescue. Here, the vertical black line showed where the thresholds was exceeded. So then you can use trace to find out what was the address at that time with a little bit of trial and error to really pinpoint what the actual instruction was. So that's really cool too. Back to AES for a final example, and shifting gears a little bit, instead of matching on a single PC address, if you're familiar with trace, you might know it's possible to get periodic PC sampling. So up to every 64 clock cycles, the trace port simply outputs a packet that tells you what the address was at that time. So instead of targeting something specific, you're just getting this, a periodic update of where you are in program execution. So here we have in black this time the same AES encryption over, in this case, because of different optimization settings that took around 10,000 clock cycles. It's running the 10 AES rounds, and you can see these at the macro level, fairly well, but you can't really tell much more than that. Now, so what we've done here is we turn on the periodic PC sampling and correlated, the PC address that came out with what function those belong to, and now we can color the waveform in the background to show what function was being run, right? So this gives you so much more information than what you had before. You can still see the 10 rounds, but now you get the breakdown. And this is really nice eye candy, but if you zoom in to, say, one of those rounds, you get a tremendous amount of information. You can see the 4 different subsets of AES and how long they take and where leakage might be occurring, and all that is now at your fingertips, right? So here you have the round key operation, the sub bytes, the shift rows, is very short, followed by the mixed columns, and then it goes to the next round. The last example that we talk about is something that, again, shifts gears a little bit, that has nothing to do with looking at power traces, so fault injection. So the idea of fault injection or fault attacks is to glitch the clock or the power of your target processor in order to alter the intended code execution. So here we're showing like a very kind of a trivial kind of a secure boot check. This checks the signature, and if it fails, it's stuck in this while loop. So you can see where this is going. While you're in this while loop, if you can glitch the processor in the right way, then you might be able to fall through and say, oh, actually, this signature is okay, let's keep going, right? And so that's something that you would want to code better as a developer to avoid a trivial kind of attack this way. So again, trace, what you could do with that is to say, well, let's get notification when we get to a sensitive operation. Now, this is not the best example for that because, of course, an endless while loop, once you're in it, you could target it at any time. But perhaps because you've coded something a bit more complicated, there's going to be specific instructions that the attacker would have to target. And trace can allow you to get notification when the code execution reaches that point and give you a semi-stable time reference to then be able to try to successfully or not, hopefully, glitch your target. Because when you want to do the glitching, here we're kind of showing what a clock glitch might look like or a power glitch might look like, and there's parameters to those glitches, right? Like how, for how wide, and so on. It's finding the needle in the haystack. So it's not something you're going to do in a single shot, but with the ETM trace, you can repeatedly try this test and sweep your parameters of your glitching to see if you're able to find one that works, or again, hopefully not, because you've coded so much better in our example here. So to finish and wrap up this presentation, I thought I should talk a little bit about what the challenges and limitations are in order to do useful things with trace. So the first thing is that ETM parsing is harder than anybody who's used it would probably like it for it to be. So the exact PC matching packet, the raw frame for that looks like this, and it's really straightforward. It'd be no problem parsing that. There's 2 bytes of header, and then you got your 4-byte address. Now, when this frame is hit 6 times in a row, so what actually happens, the raw frame that I showed earlier, that's not what comes out the trace port. This has to go through the trace port formatter, which stuffed this into 16-byte frames. Okay, that's okay. What's unfortunate about it for our purposes, where we want to match on something precise, is that every other byte will have its least significant bit stuffed into this auxiliary byte. And so parsing gets a little bit more complicated. So that's why you don't see the same thing on every line. So that means, yeah, you have to do a lot more work to parse it. There's supposed to be some color here that hasn't showed up, but I've circled here the 22, that's the auxiliary byte, and it carries information from all the other circled bytes on the first PC sync packet. So why does this matter? Well, you'd have to do the ETM parsing. You have to do that in hardware if you want to use trace to trigger immediate action, like a power trace capture or a fault injection, right? That's something that, you know, when the event occurs, you want to take action immediately. You're doing that in the FPGA. So if it's hard to parse that ETM packet, then, well, the FPGA trace logic is going to be pretty complicated. That's one of the reasons why we want, unlike the typical use case of trace where a lot of stuff comes out for the full tracing, we want to have as little stuff coming out as possible, because then it makes it, you know, still possible to trace. Now, for other use cases, like the nice rainbow AES chart that broke down where all the functions are, that's something that can be done after the fact, right? Collect your power trace, get your periodic PC samples, and treat that in software. And there's a nice software tool, open source tool called Orbiculum, which allows you to feed it the raw trace data and get, in this case, this is a periodic PC sample, and you get these spit out at you with the ugly trace formatting removed. Jitter and latency, we've talked about throughout the presentation. So the unfortunate thing about the trace port is that it puts out these synchronization frames that are 16 or 32 bits, and that's wider than the trace port, so jitter is inevitable. In this case, with DesignStart, the trace port is 4 bits wide. That gives you 6 clock cycles of jitter. So that's not insurmountable. That's something you can do in post-processing, but again, post-processing kind of limits what you can do for the stuff you need to do on the fly. Finally, latency can be very high due to that auxiliary bit decoding, right? So if your first frame comes out, you can't fully decode it until the auxiliary byte comes out, and that will be in the second frame. That could be thousands of clock cycles later. So to conclude, our objective again was to facilitate side channel evaluation so that as an implementer, you can have a better end result. Right? And by doing this early in the design cycle, that's easier to do. ARM Trace is wonderful because it's a non-invasive tool for that, so it fits into your flow much more easier. DesignStart is a great platform, right? Co-locating on the same FPGA as you did allows you to not have external pins that are toggling and to worry about, so it's all very easy to do. And I hope that we showed that with a little bit of custom FPGA work, it's possible to obtain some really nice benefits of trace that actually go beyond what some of the very expensive debug probes can do for you. And it's just really powerful, and we hope this will inspire other uses for it. Thank you.